Okay, welcome to Let's Get to the Marks. This is a question pack on the a simple atomic model. This is for separate science and combined science students. This is particularly from the AQA syllabus for chemistry. However, this is suitable if you're doing Edexcel or OCR. The content covered is the same, and this is good revision for you for your GCSE chemistry. Let's get into it. What I suggest is at the start of each question, you press pause at the start of the video, and then you unpause and watch the explanation. I'll provide the link to this pack from the fantastic Physics and Maths Tutor website in the description. All right, let's get into it. Question one. This question is about models of the atom. The figure below shows two early models of the atom. We got model A, where we have a ball of positive charge with these circles with a negative sign in them and a big plus sign in the middle there. Then we have model B with a plus sign in the circle there and some negative circles in rings around the center. Name the models of the atom shown in the above figure. Why don't you pause the video, have a go, write it down on some paper, or just do it in your head, and then I'll go through the answers. Okay, let's go through the answers. So model A is the plum pudding model. You might remember this. You do need to know off by heart the name of the person who came up with this model, and that was J.J. Thomson. And then model B is a little bit harder to come up with. It's the Bohr model, or maybe you could call it the Rutherford Bohr model, if you can spell model. Yeah. So this is the Bohr model, also known as, more commonly known as the nuclear model. So this was just after Rutherford discovered the presence of the nucleus with the alpha scattering experiment with the gold leaf. Okay, he disproved the plum pudding model. This is the next model, but this is not today's modern model. Our model's slightly different. As you know, we have other things inside the nucleus. Okay, compare model A, that's this model, with the model of the atom used today. Use the figure above. So look at that and compare it with the structure of the atom that you've been taught in school. It's worth 4 marks. Now compare. What does this word compare mean? Try to say two things that are the same. Try to say two things that are different. You can probably do 3 and 1 or 1 and 3. It doesn't really matter, but try and say some things that are the same, some things are different. You might want to write it down on a piece of paper and then test it, or just do it in your head, but try to go through and get 4 separate points. All right, I'm going to go through the answer. So you should have paused the video and had a go. Let's go. All right, I'm going to deal with similarities first of all. So both models have negative charge as electrons. So basically both models contain electrons, don't they? So that's something that's similar. Both models are spheres, but I'm going to go with differences because other than the electrons and both, yeah, both models, well, whether they'll accept this, I'm going to do like 5 things just in case. Both models have positive, uh, let's say positively charged areas. Okay, so both model have positively charged areas. So it's about similarities there. Now, what are the differences? Today's model has protons in a nucleus and neutrons in a nucleus. Um, the plum pudding does not. So there you go. There's 2 differences right there. So you probably get 4 marks for this already, but let's continue on. Today's model has electrons moving in shells or rings or orbitals around the nucleus. I don't need to put around nucleus. I'm going into super detail here. Whereas Model A, I've called it the plum pudding earlier in the question, but we could just call it Model A because you might not have identified it correctly as plum pudding, in which case refer to it as Model A. Whereas Model A has electrons embedded throughout. Now, what does embedded mean? Embedded means stuck, basically, like blueberries in a muffin or like chocolate chips in a muffin, or as they called it back in those days, plums in a pudding. And there we go. That's at least 4. There are plenty of other things we can say about them. They're both spheres. But yeah, plenty of things we can say about them. That would get you all the marks. All right, let's move on. Okay, now we've got this dude, Chadwick. His actual name was James Chadwick, but you just need to know the second name. So Chadwick's experiments showed the existence of neutrons in an atom. This led to the understanding or an understanding of isotopes. Define the term isotopes. Refer to subatomic particles in your answer. What do they mean by subatomic particles? Well, they mean like the things inside the atom. So you might need to refer to neutrons, protons, or electrons, some or all of them, or just a couple of them. Okay, define the term isotopes. It's worth 2 marks. You can do this in your head or you can write it down on paper. Why don't you press pause and have a go? Right, I'm going through the answers. So I'm going to give you the exact definition of an isotope. An isotope is an atom of an element with the same number of protons and a different number of neutrons. So in the nucleus, it's the nucleus that will be different between isotopes. They have the same number of protons, but a different number of neutrons. Now, technically, do you need to mention electrons? You don't. But if it's an atom and not an ion, it will have the same number of electrons and the same number of protons and a different number of neutrons. But you could get an isotope of an ion. And in which case, we would want to say that they could have a different number of electrons. Okay, so, but if you really want to, you can talk about electrons in this as well and say they have the same number of protons and electrons and a different number of neutrons. Now, why can I say same number of electrons? Because specifically, they talk about an atom. Atoms have the same number of electrons and protons, have same electrons and protons. Okay, so atoms have the same number of electrons and protons. However, sometimes I steer away from mentioning the word electrons and I just say the same number of protons, different number of neutrons. And the reason why is because you can have isotopes that are ions, IONS, and ions have a different number of electrons. So the correct definition is the same number of protons, different number of neutrons. But I'm just showing you some teachers mark it wrong when you say electrons. They shouldn't if you're talking about an atom. Okay, let's move on. Question 2. This question is about atoms. Atoms contain 3 types of particle: electrons, neutrons, protons. Which particle has no electrical charge? Tick 1 box. Next question. Which particles have the same relative mass? Tick 1 box. Pause the video, do these in your head, or write them down. Okay, I'm going to go through the answers. So which particle has no electron charge? That is the neutron. You can think of the N as no charge or just neutral, like the ocean, just lovely and blue and neutral, whatever. It doesn't have a charge. The electrons, of course, have the charge of -1, and protons, you can think of the P for plus, have +1. Anyway, let's move on. Which particles have the same relative mass? An electron and a neutron, an electron and a proton, a neutron and a proton. Well, the answer is a neutron and a proton. Neutrons and protons are found in the nucleus, and that is where all the mass of an atom is found. That's the hard, dense bit of an atom is inside the nucleus. They have a relative mass that we say is equal to each other. In real life, the neutron is ever so slightly greater in mass than a proton, but not by a lot. It's greater in mass by the mass of 1 electron, which is almost 0. Okay, let's zing on. Mark, mark. So let's zing on. Right. Oi, where did I go? What happened there? We flipped all over the place. So the formula of a compound is N2O. How many of each type of atom in one molecule of N2O? So how many of each time? So how many nitrogens are there and how many oxygens? That should be dead easy for you. You can do that in your head. There's 2 nitrogens and 1 oxygen. Okay, so the little number, like in H2O, you have 2 hydrogens and 1 oxygen. Or in CO2, the 2 here only applies to the atom that comes before it. So the 2 applies to the H, not to the O. And the 2 applies to the O, not to the C. Now, there's big numbers we put in front of them in equations. These are called coefficients, and that would multiply everything in here. So you'd have 6 hydrogens there and 3 oxygens there. And if I put a 2 here, that would be 2 times O2. So you'd have 4 oxygens and 2 times C, just 2 carbons. Anywho, let's move on. Right. So big numbers, small numbers, totally different things. Right, I've never heard of that. An atom of element Z contains 3 electrons, 4 neutrons, 3 protons. Give the name of element Z. Use the periodic table. Why don't you pause the video? Have a go. Okay, I'm going to go through and show you how to work out the answer. So you're going to zing over here. Right, we're looking at protons. That's known as the atomic number. The number of protons in an element tells you what element it is. So we go here, and if you have 3 protons, you are lithium. So you can see that there. In fact, let me zoom in on that. So you can see lithium has 3 protons. Okay. Um, whatever. Whatever. Look, you can see lithium has 3 protons. Nice. All right, let's go back. Zing, zing, zing. Oh, my days. What am I doing? So the answer here is lithium. So we want to type that in. And then we're being asked here, complete figure below to show the position of particles in an atom of element Z. They want us to draw neutrons, protons, and electrons. So this is going to be worth at least 3 marks, he says. Yep, so this is worth 4 marks. That is a nice question, right? So what I suggest you do is grab a pen, grab some paper, draw these 3 circles out, and then see if you can place the 3 electrons, 4 neutrons, and 3 protons in the correct places. Right. Unpause your video. I'm going to show you how to do. We got 4 neutrons. Neutrons are always found in the nucleus. Okay, so now I'm not going to draw them all together. And then protons, you've got 3. They're found in the nucleus. So there you go. 4 neutrons, 3 protons in the right places. And then we have the electrons on the shells. So I'm going to put 2 in the first shell and 1 in the second shell. Lithium's in group 1, 1 electron in the inner shell. You can only have a maximum of 2. It's impossible to have 3 in the inner shell. So you only fill up the inner shell with 2. Every other shell after that at GCSE has 8. And so let's give ourselves the marks. Bish, bash, bash, bash. Right, let's go, let's go, let's go, let's go. Zinging down, zinging down, zinging down, people. Don't forget to like, share, and subscribe. If you join my channel, I have over 700 videos on YouTube, many, many walkthroughs for combined science and for separate science, going exactly through exam papers to help you out. I also do live streams every week to help students out. Okay, right. Question 3. Discoveries in chemistry led to a better understanding of atomic structure. Atoms were originally thought to be tiny spheres that could not be divided. The plum pudding model of the atom was then developed. The figure below shows or represents the plum pudding model of the atom. So we've seen this in an earlier question. Describe the plum pudding model of an atom. Listen, a fantastic way to revise is when you're going through these is to get some revision cards and write some of these questions on revision cards and the answers on the back, because they come up again and again in exams, the same questions. And GCSEs are about learning exam technique. So describe the plum pudding model of an atom. Everybody should be able to do this. Grab some paper, grab a pen, write it down. I'm going through the answer. So you're not allowed to say it is a circle. We're going to say it is a sphere. They will give you the word if you say ball. They will give you the mark, sorry, if you say ball. So it's a ball. And what is inside the ball? It is of positive charge. So the whole ball is positively charged with electrons embedded throughout. Now you can say negative charge or electrons embedded throughout. They had discovered the electron at this time. So it's a ball of positive charge with electrons embedded throughout, and that will get you the marks. Make sure you put that on a revision card if you don't know that. Okay, an atom contains electrons, protons, and neutrons. Write these particles in the order of their discovery. This has come up twice before in the GCSE exams. So which one did they discover first? Well, you've got to ask yourself, what is it easier to discover? Something with an electric charge or something without any charge? It's much easier to discover things that have a charge. Either they're negative or they're positive. Because if you're positive or negative, you get attracted to things and you can be detected. You can create an electric signal that can be, or an electric field that can be detected. And so what we're going with, the earliest one to be discovered were the electrons. As you can see from the plum pudding model, they just knew about positive charge. They didn't know yet about protons. Protons were discovered after Rutherford did his gold leaf experiment and found that the positive charge was in the nucleus. So it goes electrons, protons, so negative things, positive things, and finally, much harder to detect were the neutrons because they don't have any charge, and that will give you a mark. And you could put that on a revision card. What is the order of the discovery of the particles? And there you go. Right, here we go. Very few atoms of the element tennessine, capital T, little s, have ever been identified. The atomic number of tennessine is 117. Predict the number of outer shell electrons in an atom of tennessine. Give one reason for your answer. Use the periodic table. Number of outer shell electrons, reason. So what we need to do is go and look at the periodic table. Now you could try to draw out tennessine by doing 2 8 8 8 8 8 8 8 8 8, but it's going to be wrong. So let me take you over. You can pause the video, have a go at this if you have a periodic table handy. If not, just watch this through. So I'm going over to the periodic table and we're going to locate tennessine. So we're looking for capital T, lowercase s. So we've got to scan. Oh my days, where are you, tennessine? And there we are. Have a look, peeps. I'm going to show you down here. Tennessine is over here. I should have really highlighted that in a different color. Let's go for pink. And you can see tennessine is there. What group is tennessine in? It's in group 7. What does that tell us about the atom? Well, it tells us how many electrons are found in its outer shell. So let's zing back over here and put our answer in. So number of outer shell electrons is 7, and the reason is it is in group 7. And there you go, 2 wonderful marks. And they're just testing you on your ability to use the periodic table. Let's look at the next one. Tennessine was first identified by a small group of scientists in 2010. Suggests one reason why tennessine was not accepted as a new element by other scientists until 2015. Right, I could come out and say that I found something else, a new element, and it's going to be a while before people agree that I have found a new element. What do the other scientists need to do? They need to do something called peer review. So they need to review the person's stuff and see if it's true. So we want to say it took time for other scientists to review the evidence. Okay, so the evidence needs to be reviewed. So we might be able to say peer review. We might also be able to say they needed more evidence. So there we go. Right, let's zing on. They probably wanted to find out if and test it themselves. So normally scientists review each other's work and test each other's work. And as a good scientist, you should publish your work and allow it to be tested by other scientists to prove your work is correct. Right, E, the discovery of isotopes explained why some relative atomic masses are not whole numbers. Element R has 2 isotopes. The table below shows the mass numbers and percentage abundances of the isotopes of element R. So the mass number of the first isotope of R is 6, and the mass number of the second isotope of R is 7. The percentage abundance of 6 is 7.6% of all of R is 7, is 6, and whatever. Percentage abundance of mass number 7 is 92.4. Calculate the relative atomic mass of element R. Give your answer to 1 decimal place. Bust out your calculator, piece of paper, pen. Have a go. All right, I'm going to go through the answers. So what they're saying from this data, it always, 99% of the time, it comes in a table like this, and they do it like that. They can make it a little bit harder sometimes. So we've got element R has a mass of 6. Element R has a mass of 7. There's only 7.6 of all the elements in the world are like that, and 92.4 of element R are the one with 7. So do we think, before we start, let's do our common sense check so we know if our answer's right. We're basically trying to calculate the average mass between 6 and 7. And you might say, that's easy, sir. That's 6 plus 7 divided by 2. That's 6.5. But hold on a minute. There aren't as many R of 6s in the world as 7s. So do we expect it to be 6.5 or do we expect it to be closer to 7? We expect it to be closer to 7. So we're looking at something like 6.9. Look, 90% are 7. So this average is going to move over towards 7. But again, it shouldn't be more than 7 because there's no R's with an 8 mass, and it shouldn't be less than 6. So you'll know you flopped if you get any numbers that aren't between 6 and 7. So this is how you do it. What you're going to do is the sum of the masses times by their percentages divided by the total percentage, which is going to be 100 in this case. So we're going to go 6 times 7.6. And then we want to add that, because we need the sum of this, to 7 times 92.4. So it's like saying if you had 100 of these elements, 92.4 of them would have a mass of 7, and 7.6 of them would have a mass of 6. That means you're going to divide by 100. And that is going to give you your mean mass. And we need to do it to 1 dp. Let me grab my calculator. You can do that in your head. You are a genius. Right, 6 times 7.6. That gives me 45. So if I did these individually, it would end up like this, 45.6. And then I would be adding that to 7 times 92.4. If I didn't keep these all in my calculator, I'd be adding that to 646.8, and then I'd be dividing by 100. So let's try this out. Ba, 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 divided by 100. It equals, I'll give you the answer here, guys. It's 6 point, oh my God, 6 point, I can't write properly, 924. So they want this to just 1 dp, one decimal. So do I round this up to 7.0 or 7.1 or round it down to 6.8? No, look, the 2 is lower than 5. So I keep it as 6.9, and that is going to get me all of the marks. So 1 mark for setting out the equation, diddly-dee, 1 mark for getting the answer, and 1 mark for rounding to 1 decimal place. 3 beautiful marks. Right, let's move on. Okay, let me shrink this down so we can get this whole question in. Right, question 4. This question is about atoms. The figure below represents an atom of an element. We've got neutrons, we've got protons. It looks like we've got electrons. Oh dear, I've kind of given the game away, haven't I? So let's look at this. Question 4. This question is about atoms. The figure below represents an atom of an element. You can see A, B, C, and D. What you've got to do is draw one line to each name to the correct label. So can you label that? What I would do, as it's practice, revision, try and see if you could label all of this. Now, a really good way to do this on a revision card, copy this out onto a revision card on the front, and then put label this on the front. Now, on the back, copy it out again, or just write the letters and the names of each thing. And that is the best way for you to learn this kind of content. So I'm going to go through it. Well, A is an electron. What is B? B is a neutron. How do I know B is a neutron? It doesn't have a plus or minus. D is a proton because it begins with a P and protons are positive. And C is really, it should be called a shell. Some people will allow you to call it an orbital. Well, the example will allow you to call it an orbital. So it's an energy level, shell, or orbital. And now let's match them up. So which one is a neutron? Well, a neutron was B. Which one was a proton? Well, a proton was D. And that will get you 2 fat marks. But like I say, I reckon drawing a blank one of these and then on the back, writing down A, B, C, D and putting the names would be a fantastic revision card for you to make. Active learning, and it'll be really useful for the future. Make sure you label, if your revision cards are chemistry, you put a C in the top left or right hand corner of the revision card, and this will allow you to know that goes in your pile of revision cards for chemistry. All right. B, an atom of element Y has an atomic number of 9, a mass number of 19. Give the number of electrons and the number of neutrons in this atom. Choose answers from the box. So Y has an atomic number, by the way, pause the video, have a go in your head. Right, an atomic number of 9. We write the atomic number at the bottom and the mass number at the top generally. Okay, in AQA we do anyway. In OCR they sometimes flip it around. So what is the number of electrons and neutrons? So the number of electrons, well, this is protons, and protons are always equal to electrons. So there are 9 electrons. The mass number is actually made up of protons and neutrons in the nucleus. So I want to do 19 minus 9. This is going to have 10 neutrons. And that is going to get you all of the marks. Right, let's move on. Oh, we got another isotope one. Wunderbar. The table below shows the information about two isotopes of element Z. We've got isotope A, mass number of 39, percentage abundance 93.3. Isotope B, mass number of 41, percentage abundance 6.7. Calculate the relative atomic mass AR of element Z. Use the table and the equation. They've given us the equation. That is beautiful. And they want the answer to 3 sig fig, not one decimal place this time. It's 3 marks. Why don't you pause the video, grab your calc, grab your pen, grab your paper. Okay, I'm going through the answers. So what we want to do here is just put a times in between these and add them together. So we want to go 39 times 93, excuse my writing, 0.3. I'm going to smash that in the calculator. So 39 times 93.3, and that gives me 3,638.7. Now, even if you flop the hard on the rest of this, you can get some marks because what we're going to do the next one, which is 41 times 6.7. And we're going to go plus, oh no, we're not going to do that. We're going to go, what did we say that was? 6.7 times 41. Jeez Louise, man. That equals 274.4. And we want to add these together now. So we're going to plus that to 3638.7. And we're going to get total is 3913.4. So for your working out, you're going to get marks. Now we need to divide this by the total abundance, which is 100. So we divide that by 100, and we're going to go divided by 100 equals 39.134. Now what I say is do the common sense check. What's the common sense check? The common sense check is to come up here to your data and say, look at the mass numbers. Isotope A, if you had 100 of them sitting in the room with you right now, 93 of the 100 would have a mass of 39, and only 6 or 7 would have a mass of 41. What do we expect the average mass to be closer to, 39 or 41? We know it has to be in between these two masses. And look, it's closer to 39. We're bang on, right? So this is common sense check, just in case like you get some weird number like 56 or 105, then you'd know, well, hold on, it has to be in between 39 and 41, and it should be close to 39. Okay, anyway, enough of that business. We need to do the 3 sig fig. You see it says 3SF over here. So 3 significant figures don't include zeros, just include the first 3 numbers. So 3, 9, and 1. Do we need to round it up? No. If that was 5 or above, we'd round it to 392, but we're going to keep it as 39.1. So basically it ends up being like 3 decimal places. So 1 for any of your working out successfully done there, 1 for the answer, 1 for the correct rounding. Right, let's zing on. Okay. D, suggest the identity of element Z. Use the periodic table. Element Z is, well, we need to look at the proton number of element Z. We have the mass number. Oh, actually, we've worked out the mass was 39.1. So what we need to do, did they give us anything else about element Z up here? No, this was all element Y. None of this was element Z. So the only thing we can go on is the mass number. We don't have the number of protons. So what we're going to do, we're going to go to our periodic table and we're going to look for something with a big number, a mass number of roughly 39. Now notice I'm going all the way, look, 35.5, 40. Oi, 39 looks like it is going to be potassium. Yes, it was 39.1, so it was close to potassium than it was to, yeah, it's going to be potassium. It can't be calcium. Okay. Right. So element Z, folks, is going to be potassium. Complete the sentence. Choose the answer from the box. Electrons, neutrons, protons. Isotopes of the same element have a different mass number because the isotopes have different numbers of. So isotopes have different numbers of neutrons. If they had different numbers of protons, their atomic number would be different, the little number at the bottom, but it's just the mass number that's different. So the correct answer is to write neutrons in here. Okay, that would get you to mark, and that would get you to mark. Let's zing on. Don't forget to like the video, guys. It massively helps me out. If you press pause, hit the like, it makes me want to do more videos to help you smash your GCSEs. This question is about elements, compounds, and mixtures. Which type of substance is hydrogen? Pause the video, have a go. Right, hydrogen is only made up of one type of atom. Yes, hydrogen is bonded two H's together. It's a diatomic molecule, but hydrogen is an element because although it's made up of two atoms, they are identical. So hydrogen is an element. Right, let's zing down. We've got more testing on elements, compounds, and mixtures down here. So let's zing this. The diagrams in figure 1 represent different substances. Gray, black, and white circles represent atoms of three different elements. Use figure 1 to answer parts B and C. So why don't you, the first question is, which diagram represents a mixture of compounds? Which diagram represents a mixture of elements? It's worth 2 marks in total. Why don't you pause, have a go? All right, I'm going to go through the answer. So a compound is essentially something made of two or more different atoms. So which one is a mixture of compounds? This is just a pure compound. So this one is just a compound, right? This one, well, this is a compound and this is an element, okay? So this is a compound and that is an element. So this is a mixture because they're not joined together. So that is a mixture of compounds and elements. Now over here, this is an element and this is a different element, but notice they are not joined together. So this is a mixture because they're not chemically bonded, a mixture of elements. And then the final one over here, we have one type of compound and another compound. And so this is a mixture of compounds. And now it should be dead easy for you to work out. And again, what you could do is copy this exact diagram down on the front of a revision card and put the questions, which ones you could actually say A, B, C, D, and you could say which one is a mixture of compounds, which is a mixture of elements, which is a mixture of compounds and elements, and which one is compounds only. And then on the back, you could write the answers. That would be a fantastic revision card to help you. Right, which diagram represents a mixture of compounds? It's this one, A. Which diagram represents a mixture of elements? It's this one, B. And that is going to get you both of the marks. Let's go. Okay, these are all exam questions from the last 6 years of GCSE exams. Substances can be separated from mixtures by using different methods. Complete the sentence. Sand can be separated from a mixture of sand and water. So this is nice and easy. Pause, have a go. It's filtration. A mixture of 4 liquids were fractionally distilled. Figure 2 shows the apparatus. We've got a thermometer, we've got a mixture of liquids, we've got an electric heater, we've got the water coming in here and working its way up here and then shooting out there. This is called a condenser. We've got a beaker, we've got distilled liquid down here, and we've got the boiling points of A, B, C, and D, 97, 138, 78, and 118. Let's go down and find out what the question actually is. So we have a question here. Which liquid in the table would distill and be collected into the beaker first? So which one will turn back into a liquid first? We boil them all and we evaporate them all. Which one is actually going to turn back into a liquid first? Think about it. If we heat them up really high, say to 150, then it starts cooling. It's actually the one with the lowest boiling point is going to condense the fastest. So the one with the smallest boiling point is going to condense the fastest. So we want to say it is going to be 78. No, not 78. It's going to be C. Basically, the first one to become a gas is C because it boils at 78, comes up here. Then it comes down here, turns back into a liquid. All of the others will stay in here as a liquid. When the temperature hits 97, A will come off and come down. When it hits 118, D will evaporate, hit here, turn back to a liquid. And then the last one to come off will be B. So you get the idea, right? Cool. Suggest what would happen to the temperature of the water as the water flows through the condenser. So what they're saying is, now the water isn't in contact with these gases coming out here. It's just flowing in here. So the water comes in and it's round the side of the tube, keeping it cold to make the gases condense. And as the water flows around the tube, it pours out and goes down your sink there. So it comes in there and then goes out there. What do you think the temperature of the water is like here compared to here? Well, it's taken some of the heat from these gases in order to condense them back to liquid. It has absorbed their heat. So the temperature of the water is higher. The temp is higher as the water flows through the condenser. The temperature changes, it gets higher, it increases, and that is going to get you the marks. Right. Bosh bish. We must be coming near the end. Oh gosh, gone a bit far. Describe how to obtain sodium. All right, let's read that again. Rewind. Describe how to obtain sodium chloride crystals from sodium chloride solution by crystallization. So what they're saying is you have a beaker, and in the beaker you have water particles like this, and you have some salt particles of sodium chloride. So what I'm going to do here is draw your crusty little salt particles. So here is my NaCl. How do we get these out by crystallization? Well, the first thing we're going to do is heat it gently using a water bath. And there's a reason why we heat it gently. We don't want to boil it vigorously with a Bunsen burner. So we're going to heat gently, which will evaporate some of the water. And then we tip it in. Once the crystals start coming out, we tip it into a little evaporating basin and we leave in a cool area for it to crystallize. And that is what we do. So you need to know this. I would put it on a revision card. How do you carry out crystallization? I just write the word, what is crystallization? So we say heat gently, evaporate water. It's how you get a soluble solid away from a solution is crystallization. And this is the method. Heat gently, evaporate water, then leave in cool area to crystallize. And technically, if it wanted you to know how to get dry crystals, I would say then dry with paper towel. Now, but it didn't say dry crystals. Sometimes they say how to get pure and dry, but yeah, didn't say that here. So there we go. Bosh. Is that the end of the pack? What's up, Jack? That's the end of the pack. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. I'll catch you lot on my next video. Let's get to the marks.
You're still here? It's over.